Welcome to The Explainer. You know, energy is literally the ultimate shapeshifter in our universe. It never actually disappears. It just goes into hiding or puts on a new disguise. So our job today is to play the energy detective, track it down, and demystify the completely fascinating world of thermochemistry. To kick off our investigation, let's look at the big picture. Have you ever just stopped and wondered where over 90% of the energy we use actually comes from? We're talking about a massive scale of thermochemical reactions happening constantly, shaping literally everything around us. Well, the ultimate answer is the sun. Every single day, the sun hits the Earth with almost 10,000 times the amount of energy we need globally for all our demands. And we interact with the solar energy every day, usually without even realizing it. Whether you're grabbing a cheeseburger for lunch, burning fossil fuels while you're stuck in traffic, or relying on materials like iron and aluminum from heavy industry, you are interacting with stored solar energy that's being released through chemical changes. All right, here's our roadmap for today's investigation. 1. What is energy? 2. Heat, temperature, and capacity. 3. The science of calorimetry. 4. Internal energy and enthalpy. And 5. Hess's law. Section 1. What is energy? Tracking the invisible. At its very core, energy is just defined as the capacity to supply heat or do work. But what's super cool is how it constantly shifts forms. Think about Victoria Falls for a second. Water sitting way up at a high elevation holds a ton of potential energy, just because of its relative position. But as that water plummets downward, like you'd see flowing through the generators at the Hoover Dam, that potential energy instantly converts into kinetic energy. That's the energy of motion, which is then used to do work and generate electricity. It's just a constant flowing transition. Which brings us to the absolute golden rule of our investigation, the law of conservation of energy. It states that during a chemical or physical change, energy can neither be created nor destroyed. It only changes form. Period. So when gasoline burns in your car's engine, that chemical potential energy doesn't just vanish into thin air. No way. It rapidly expands as gaseous products to push the pistons, converting right into mechanical kinetic energy. Every single drop of energy is accounted for. We can always track it down. Moving on to Section 2, heat, temperature, and capacity. Now, people mix these two up all the time. Thermal energy and temperature are definitely related, but they are distinctly different concepts. Thermal energy is the total kinetic energy from the random motion of all the atoms and molecules in an object. Temperature, on the flip side, is just the average kinetic energy. It's simply our way to put a number on how hot or cold something is. If we zoom way into the microscopic level, you can really see this in action. Hot water molecules are vibrating frantically. They have a really high average kinetic energy. But cold water molecules, they're super sluggish. When these two interact, heat, which, by the way, is just the transfer of thermal energy, flows spontaneously from the hyperactive hot molecules right to the sluggish cold ones. And this flow keeps happening until they all hit the exact same average kinetic energy, a sweet spot we call thermal equilibrium. All right, let's clear up another common mix-up: heat capacity versus specific heat. Heat capacity is what we call an extensive property, meaning it depends entirely on how much matter you actually have. Think of cast iron frying pans. A massive, heavy pan has a way higher heat capacity than a tiny little pan, simply because there are more atoms to heat up. However, their specific heat is an intensive property. That means it only depends on the type of substance. Because both of those pans are made of the exact same cast iron, their specific heat is completely identical. To put some numbers to this, just compare water and iron. Water has a remarkably high specific heat of 4.184 joules per gram degree Celsius. Iron? It's way down at 0.449. Think about what that actually means. It takes almost 10 times more energy to heat up a gram of water than it does a gram of iron. That right there is exactly why a metal seatbelt buckle will literally burn you in the hot summer sun, but a bottle of water sitting right next to it is still reasonably cool. So how do we track this mathematically? We use a neat little equation. Q equals m times c times delta T. The heat transferred, that's the Q, equals the mass of the substance times its specific heat times the change in temperature. If we can pin down these three variables, we know exactly how much energy entered or left the scene. Section 3, the science of calorimetry. So how do we physically capture and measure this energy in a lab? Enter the calorimeter. This is our ultimate investigative tool.
It isolates a chemical reaction, which we call the system, from the outside world. The liquid inside the calorimeter acts as the immediate surroundings. In an exothermic reaction, the system releases heat, which warms up the surroundings. In an endothermic reaction, it absorbs heat, cooling the surroundings down. Because the calorimeter is so incredibly well insulated, the net heat change is practically zero. So the exact amount of heat lost by the reaction is perfectly equal to the heat gained by the surrounding water. We measure the water's temperature change, plug it into our Q equals mc delta T formula, and boom, case closed.
Now, a simple constant pressure coffee cup calorimeter works perfectly fine for standard reactions in a solution. But what if you're dealing with a vigorous combustion reaction that would literally blow the lid off a coffee cup? That's when you pull out the constant volume Balm calorimeter. The steps are pretty straightforward. First, you submerge a super robust steel container, the Balm, into water. You load in your sample with high-pressure oxygen and then hit it with an electrical spark. The thick steel absorbs that massive explosion of energy safely without expanding at all, transferring the heat right into the surrounding water for us to measure with total accuracy.
Section 4. Internal energy and enthalpy. Okay, time for the first law of thermodynamics, which comes down to a really elegant equation. Delta U equals Q plus W. In plain English, this just means that the change in a system's internal energy, U, is perfectly equal to the heat absorbed by the system Q plus the work done on the system, W. And in chemistry, work usually just means expanding gases pushing back against atmospheric pressure.
Now, to really get thermochemistry, we absolutely have to talk about state functions. A state function is a property whose value depends only on the current state a system is in, regardless of how it actually got there. Now, this is crucial. Heat and work themselves are not state functions. Their values completely depend on the specific path you take during a reaction. But internal energy, that absolutely is a state function.
Let's ground this in a real-world analogy. Picture two people hiking up Mount Kilimanjaro. They take completely different trails to the top. One is a direct, steep climb. The other is an incredibly long, winding path. The total distance they walked is totally different, right? That means distance walked is not a state function. But their final altitude? They are both standing at exactly 5,895 meters. Altitude only depends on their final position, completely independent of the crazy paths they took. So altitude is a perfect example of a state function.
And that brings us right to enthalpy, represented by a capital H. Enthalpy is defined as a system's internal energy plus the product of its pressure and volume. And just like internal energy, enthalpy is a state function. Now, why do chemists absolutely love this term? Because if you run an experiment in an open beaker, meaning atmospheric pressure stays constant, the change in enthalpy is exactly equal to the heat flow. It makes calculating heat changes in everyday open-air lab setups incredibly straightforward. Finally, Section 5, Hess's Law. Here is where the absolute magic happens. Hess's law. Because enthalpy is a state function, the total enthalpy change of a chemical reaction is completely independent of the specific steps taken to get there. Sound familiar? That's just like our mountain climbers. This means if we have a totally new, highly dangerous, or just extremely difficult reaction to measure in the lab, we don't actually have to risk doing it. We can literally just look up the enthalpy values from known, simple reactions in a reference book, add them together mathematically, like a giant puzzle, and figure out the exact heat of our complex reaction. Which leaves us with this question to ponder. How can we calculate the exact energy of chemical reactions happening on distant planets without ever leaving Earth? Well, the answer is right in front of us. Because the laws of thermodynamics are universal, and thanks to the predictive power of state functions and Hess's law, we can calculate energy transfers anywhere in the cosmos just by crunching the numbers. Thermochemistry isn't just about hot and cold water in a lab. It's the mathematical master key to understanding the energy of the entire universe. Thanks for joining me on this explainer, and keep tracking down those invisible forces around you.